Okay, so today I'm just going to lecture the whole time. So let's talk about section 10, monotone sequences. Seems like you all have already looked at this section, or yeah. Seems like you've looked at this section already. So maybe you can tell me what monotonic sequences are. What are monotonic sequences? Julia.
They're sequences that are either never increasing or never decreasing.
Okay. So there's basically four types: increasing, non-decreasing, decreasing, and non-increasing. Okay, so increasing means, of course, that the next guy is strictly bigger than the last guy, right? That for all n, for each n, a sub n plus 1 is strictly bigger than a sub n, right? Non-decreasing means that it's bigger than or equal to, right? So it could be flat, but it cannot be dropping, right? It could be flat, not dropping. Okay. Decreasing means that the next guy is strictly less than this guy, right? And non-increasing means that well, it could be flat, but it's not getting bigger. Okay. So these are terms that you apparently have seen before. Okay. I should say that people sometimes use a different terminology. They call this increasing, and they call this strictly increasing. Right, and they call this decreasing, and they call this strictly decreasing. I actually like that terminology better, because then you don't have to think the sort of non-decreasing. What does that mean? You're not decreasing. There's no double. There's no thinking involved with it, right? Increasing means that you're getting bigger. Strictly increasing, you're strictly getting bigger. So I tend to use that terminology. Okay. Right. So there's four kinds of sequences, 4 types of monotonic sequences. These are the. Okay. So we have this thing called the Monotonic Sequence Theorem, which again you apparently have seen before. Tell me about it. What does it say? Monotonic sequence theorem. If your sequence is monotonic, then
sequence converges.
Bounded monotonic sequence converges. So, right. So you've got S sub n, a monotonic sequence, Sn bounded implies that Sn converges. Let this be a monotonic sequence, then boundedness implies convergence. Okay. What about the opposite direction, convergence and boundedness? Does convergence imply boundedness?
Yes.
Yes, it does, right? For monotonic sequences, or
Just all sequences.
all sequences, right? So in fact, this is an if and only if, right? It's just that the only if is not that interesting. We knew that already. Okay, so the main point of the monotonic sequence theorem is that boundedness implies convergence. Okay, so this part is done before. Okay. And how do you prove it? Let's suppose we have is a a non-decreasing sequence. Non-decreasing bounded sequence. Why do we know it converges? What's the gist of the proof? We sketched it out last time in class. Can somebody remember or tell me?
The least upper bound.
Least upper bound,
Yeah.
exactly. Right. So you say, well, look, the terms are bounded, so there exists a least upper bound. Right. Least upper bound. Call that thing S. Right. Then we claim that that the Sn actually converge to S. Right? Right? So here's S, and what we're saying is that the S of n have to, these are increasing sequence, they're going to converge to S, right? In other words, given any epsilon, we can find a time past which they're inside this thing. Okay. And can anybody, somebody else tell me how we show that? We take this epsilon neighborhood here. How do we know that everybody past some point, everybody's inside there? First off, how do you know that any element is inside there?
Because of the least upper bound. If it wasn't the least upper bound, like if there was no element between S and S minus epsilon, then S would not be the least upper bound.
Right. Okay. So, right. So, given epsilon, if the interval S minus epsilon, S plus, epsilon contains no element of S of n, then there's a contradiction, right? S would not be the least upper bound, not the least upper bound. Okay, so we know that this interval S minus epsilon, S plus epsilon contains some S of n naught. Right? But then, for all n bigger than that n naught, S of n is contained in the interval. Right? Because S of n, right? Since S of n naught is bigger than S minus epsilon, and S of n is bigger than S n naught, since it's increasing sequence, right? Right. So this S of n is trapped between S minus epsilon and S plus epsilon. Okay, right. So the idea is simple, right? You just say, well, look, we know that one of these guys has to be inside there, because if not, that's not the least upper bound, right? But then we know everybody else is higher than that and lower than S. So they're all, everybody past that point is inside there. Right? So that's what we're saying. Everybody past that point is higher than that and less than S. So they're contained in the epsilon neighborhood of S. Okay. Does that make sense? Right? It's easy. Right? Okay. Okay, so I'm going to just state one more theorem. I'm not going to prove it because I want to get on to more interesting things. But it's an easy one. If S of n is monotonic and unbounded, then S of n goes to plus infinity or S of n goes to minus infinity. So monotonic and unbounded means you go to infinity. But that's, you can sort of imagine why that's intuitively that's obvious, right? If it's increasing and unbounded, it's going to go to infinity. If it's decreasing and unbounded, it's going to go to negative infinity, right? The proof is easy. Yeah, Marco.
But if it's not, if it's one of those that doesn't have to be greater than, couldn't it still also, it's unbounded?
Unbounded, right? So the unbounded means that there's no number that it's trapped between, right? There's no number m so that it's trapped between m and negative m. So right, so no matter what number you give it, it's going to exceed it at some point.
Good.
Well, then, yeah.
So, say there's a sequence A of n that was all, that for every value in the sequence it was 1. That would still, do we still say that even though that sequence is monotonic, but then it would be bounded.
Yeah,
it would be
that's
bounded.
bounded, yeah.
Yeah.
Okay. Good. Okay. So I'm gonna jump a little bit to something. Okay. So I'm gonna. Okay. So we're going to talk about something called the Bolzano Weierstrass Theorem. Okay. And so the way I'm going to present this will be a little bit different. It will be somewhat different from the way that the text presents it. If you want a reference for this, there's a book by a guy whose name I cannot pronounce. It's called A Friendly Introduction to Analysis. And I think maybe I got this from there. I don't remember. Okay, at least I have it written down here. That probably means I got it from there.
Is this a different section?
This is the same section. It's still section 10. Section 10 has a lot of stuff in it. Okay, so first off, some definitions. One you've seen before. So if you have a point in the real numbers and some number r bigger than 0, let n sub rp denote the interval all real numbers that are within R of P. Okay. All numbers whose distance to P is less than R. Okay, this is called a neighborhood of P with radius R. And of course, you see what it is, right? There's some point P, there's some distance R, right? And it's everything between here and here, right? In other words, it's just the interval P minus R, P plus R. It's the open interval P minus R, P plus R. So we call this thing the neighborhood of P with radius R. Okay. This definition actually we'll use it in higher dimensions. That's why they call this thing a radius. Right? In higher dimensions, it would be an open ball, open disk centered at P, or an open ball centered at P in 3 dimensions. Okay. So that's the first definition. Let nRP star be everything, basically the same thing, but you don't allow x to equal p. Okay, so the distance cannot be 0. Everything whose distance is less than r but bigger than 0. Okay, so the picture is you've got P, you've got your open neighborhood, but you don't allow this center point. You don't allow this center point. Okay, and we're going to call this a punctured neighborhood. And I almost never write the word neighborhood. Okay, I always will use some abbreviation. Okay, so it's a punctured neighborhood. Okay, so here's a more complicated definition. Let S be a subset of R, and let S naught be in R. Okay, so you've got some subset in R, and you've got some point in R. If for every epsilon, the punctured epsilon neighborhood of S naught intersects S. Then we call S naught an accumulation point. Of S, or a cluster point in some texts. It's called cluster point. Okay, so this is saying that every punctured neighborhood of S naught intersects S. Every punctured neighborhood of S naught intersects S, right, in English. Every punctured neighborhood of S naught intersects S. Okay, so for example, let's say that S is the set of points 1, 1/2, 1/3, 1/4, blah, 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 right? So 1 is 0, right? 1, 1/2, 1/3, 1/4, 1/5, 1/6, blah, 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 right? You got all these points, right? And you see that 0 is an accumulation point of S. Right, for this S. Right, because if I take any neighborhood of any punctured neighborhood of 0, it intersects S. Late but well dressed. Right? Do you guys see that? Right? Any punctured neighborhood of 0 is going to intersect S. Okay, so 0, right? No matter how small a neighborhood I take, it's still going to intersect S. right? There'll be some point of S inside that punctured neighborhood. Okay. Are there any other accumulation points? Does this S have any other accumulation points? So an accumulation point, okay, so accumulation point means that okay, so here's, well,
It's okay.
Okay.
I'll read it back.
Okay, good. Okay. So are there any other accumulation points? Marco.
Isn't every point to the right of 0 also an accumulation point?
So is 1 an accumulation point? Is 1 an accumulation point? To be an accumulation point means that every punctured neighborhood has to contain some element of S. So you'd say, well, look, if I take this neighborhood, it contains elements of S. But does every punctured neighborhood? No, because if I take this punctured neighborhood, I'm not allowed to count that point in the middle.
Yeah.
Okay. If I take that punctured neighborhood, well, there's nobody of S inside it. Right? Right. So none of these points here are accumulation points. Okay. None of these points here are accumulation points, right? Nor is anything like this, right? Like this is not an accumulation point, right? Okay, so no points except for 0 is an accumulation point. Are accumulation points. Okay. Second example. Let's say that S is x1 through xn in R. Okay, so x1, x2, xn. There's a finite number of points, right? What are the accumulation points of this set? What, if any, Nick?
Sorry, the question is
Sure.
n only integers?
Yeah, n is a finite integer. So, okay. So like, there's a finite number of points. There's a billion points here. Okay. There's a billion points here. What does this set have any accumulation points, Nick?
Would all of it from x1 to xn be an accumulation?
It only makes sense to say, are you saying that each one of them is an accumulation point?
Other than x1 and xn, because in theory, if they're finite but still there's like a lot of them, you could take any point and you could put a different x n minus 1 in there.
Okay, so an accumulation point means that no matter what neighborhood you take of it, if you consider the punctured neighborhood, that is the neighborhood excluding the center point, then that interval intersects your set. To be an accumulation point of a set means that here's our example, right? Here in this example, every interval containing 0, every punctured interval, right, containing 0, intersects this set. Okay. So what do you see? That there's no accumulation points, right? There are no accumulation points because you could always take, some sort of minimal distance, right? You could whatever. If I pick this guy and then I choose epsilon to be the closest distance to the next point. Right? The smallest distance to the next point, well, that's not going to contain anybody. That punctured neighborhood is not going to contain anybody in my set. Is that clear? Yeah, Julia.
So do only convergent sequences have accumulation points?
Well, suppose I have something like suppose I have a set, I have a bunch of points that go like this. They walk backwards and they walk forwards. Right? They sort of go backwards and forwards and backwards and forwards. Well, that set's going to have accumulation points, but it's not going to. Right? And suppose I have a sequence that goes like this. it says, give me 1 minus 1 over n and 0 plus 1 over n, right? So they would be, this wouldn't converge, right? So like, let's say like these are the odd terms, and these are the even terms. Okay. Well, then the even guys would converge to this thing, and this number, and one would be an accumulation point, and 0 would be an accumulation point, but this wouldn't be a convergent sequence. Yeah, Aria.
So I guess we said that there has to be at least one bound for there to be an accumulation point.
What do you mean by a bound?
So for example, the upper one that we did, where 0 was the accumulation point,
Yeah.
it was bounded below by 0.
Yeah.
And so 0 is the accumulation point. Or like for this one that you're talking about, like all the elements are within those two.
That's true, but you could have guys that keep on going farther and farther. In like, suppose you like every 10th term you make them go outwards, right? These would still be accumulation points, right? But let me do some more examples, and then before you, hopefully that'll clear up some questions before we. Okay. So okay, example 3. S being the half open interval 0, 1. Okay. What are the accumulation points? What are the accumulation points? We got this. Here is 0, here is 1. What are the accumulation points? Nick?
Wouldn't it be all of them?
All of
within the set.
everybody in the set?
Yeah.
Shh, okay, yeah. Certainly, any point in the set is an accumulation point. That's true.
Isn't 0?
And 0. Right? And 0 also, right? Because if I take any punctured interval around 0, it intersects the set. Right? I can't avoid intersecting the set. Okay. And that's it, right? If I take anybody else, well, I can find some interval that doesn't intersect the set at all. Okay. Last example. The rational numbers. Julie.
All rational numbers would be accumulation points because of the theorem that says it's infinitely dense.
Okay. So all rational numbers, right? If I take any rational number, yeah, because if I take an interval here, right, p over q plus epsilon, p over q minus epsilon, I know by the density theorem that there's rational points inside there, right? So certainly any point in the set is an accumulation point. That's true.
Also, could you say any element of the real numbers?
Yes, right. In fact, any number is an accumulation point, right? The accumulation points are the whole real line, right? Because the density theorem says that between any two real numbers, you've got rational numbers, right? So here I've got my two real numbers. Then I'm guaranteed to have some rational numbers inside there. Right? So this thing is going to intersect the rational numbers. Okay. Any questions on this idea of accumulation point? I hope it's getting kind of clear now. This is what's called a topological. This kind of definition is from something called point set topology. This is a topological definition. Those of you who have been in my class before know that you probably heard me talk about this, but there's a hilarious YouTube video called "Hitler Learns Topology," so they've taken some World War II movie where Hitler is addressing his generals and his people, and he's really frustrated. I think things are going really badly for him, and he's like talking, like, he's very expressive. He's furious with them. Things are going really badly. But they've dubbed it over. I'm sorry, they've subtitled it. It's in German. Right? So unless you understand German, it means nothing to you. Right? But so people have taken it and subtitled it, and they've subtitled it as Hitler's trying to learn topology, and he's talking to a group of topologists. And he's like saying, how you are supposed to be the finest topologist in the country, and yet you cannot come up with a good definition. How is anybody supposed to make sense of this? How do I know the difference between accumulation point and a cluster point? He's really angry. He says, the way you define open sets, it seems as if it could be open and closed at the same time, right? And then there's one person shaking, and he says, "Mein Führer, actually, that's possible." Those are called Klopen sets. And then he's like, "I can't believe this bullshit." And everybody's like, "Oh my god!" And they're all, and like, don't worry. They're trying to calm each other down. Anyway, I recommend it. Okay. Okay, so this leads up to something called the Bolzano Weierstrass Theorem. For sets, maybe. We'll do two kinds of Bolzano Weierstrass Theorem. Okay, so let S be a subset of R if S is bounded and infinite, then S has at least one accumulation point. So any bounded infinite set is guaranteed an accumulation point. Okay, and that sort of makes sense, right? You're thinking like, well, your set is trapped between two values, right? Your set is trapped between two values, and there's infinitely many of them. There's infinitely many different points in here, right? Well, they've got to clump together at some point. There must be some point in there where they start clustering. Okay, right, so this is the Bolzano Weierstrass theorem. The proof of this, just for another entertaining thing, there's a paper called a contribution to the mathematical theory of big game hunting, which is kind of a joke paper, but it's published. I forget in what journal. It's like from the early 20th century, when people had more of a sense of humor, maybe the editors had more of a sense of humor. So they say, well, suppose you know that there's a lion in a field, right, and you want to catch the lion, and they give all sorts of different ways, all sorts of different mathematical ways of catching the lion. Like they say, draw a circle around yourself, and then apply an inversion to the field, and then you'll be on the outside, and the line will be on the inside. Right? Do an inversion across the boundary. The one that's related to the Bolzano Weierstrass theorem is, they say, cut the field in half, and then see what field the line is in. Cut that field in half, and then see what field the line, see what part the line's in. Keep on continuing until the lion is in a cage. The lion is in a cage that's so small he cannot move, and then just take him away. Right. So, and this is actually the proof of the Bolzano Weierstrass theorem. Okay. So, okay. So we have enough time to do it. So say okay, S is bounded. So we know that S is contained in some interval A1, B1. Let's call that thing I1. Like for some A1 less than B1. Okay. Express I1 as A1, C1, union C1, B1. Okay, so chop I1 into two parts, right? Chop I1 into two parts where C1 is the midpoint, A1 plus B1 over 2, the midpoint. Then you know that one of these intervals contains infinitely many, so I should say at least one of these intervals contains infinitely many points of S, right? Right? Because if they both contain finitely many points, that means that your set is finite. Right? So one of these intervals has to contain infinitely many points. Note it as I2 and call its endpoints A2, B2. Okay. Continuing in this manner, continue in this manner. Right? We obtain a sequence of intervals, a sequence of closed and bounded nested intervals. Right? Nested intervals, I1 contain I2, contain I3, blah, blah, blah. Right? Well, you know what I'm going to do. Right? Right? So you've got these closed and bounded nested intervals where the length decreases, right? The length of the nth interval is the length of the initial interval, the length of the initial interval divided by 2 to the n. And 2, each in contains infinitely many points of S.
What's n?
N is any natural number. Right, so I2, the length of oh, this is not right. Let me call this guy I0. I guess I should have just written n minus 1. That would have been easier. Anyway. Okay. Okay, so what am I going to do next? How do I find my accumulation point? You just handed in the homework. What are we going to do? We've got this sequence of closed and bounded nested intervals.
Take the intersection.
We're going to take the intersection, right? So, plane. The intersection is a single point. Call it A. Okay. The proof is, well, you already did in your homework. In your homework, you showed that the intersection is non-empty, right? So you know the intersection is non-empty. You prove that using the completeness axiom, right? And there could not be 2 points since the length of the intervals, I didn't explain that. Sorry, this says the length of the interval, right? When I write like the absolute value of the interval, that actually means the length of the set. It's what's called the measure of the set. Right? The length of the intervals goes to 0, right? As k goes to infinity, so there couldn't be 2 points in there, right? If there are 2 points in there, then, you know, at some point your interval is going to be shorter than the distance between those 2 points, right? That's impossible. Right? It leads to contradiction. If there are 2 points in there, well, then there's some distance between them, but then how does the length go to 0? Okay, so, right, so what you do, right, you have your interval, I naught, you divide it in half, and you say, which half contains infinitely many points? Okay, let's take that guy, call that I1. You divide that guy in half, you say, which half contains infinitely many points? If there are 2, you just choose maybe the left one, whatever. Right, and you keep on going, dividing in half each time. Okay, so you get the sequence of intervals nested that descend to 0, whose lengths descend to 0, and you take the intersection, you get a single point, right? Call that point A. And our claim is, of course, that A is an accumulation point. A is an accumulation point for S. Okay. Well, to be an accumulation point means that you're given any punctured neighborhood of it that contains infinitely many points of S. I'm sorry, it contains a point of S, right? So, want to show that given any punctured neighborhood of A, it intersects S. Okay. So you say, okay, well, come here. So let's say that our point is here. Okay. Let's say that our point is here, and somebody says, can you show me that this punctured neighborhood, they give you a punctured neighborhood. They say, can you show me that this punctured neighborhood contains elements of S, not including possibly the middle? Right? Well, why would it contain elements of S? Well, think about these intervals that you've chosen, right? The intervals you've chosen contain infinitely many elements of S, right? This interval contains infinitely many elements of S. This interval contains infinitely many elements. This interval contains infinitely many elements. And say, oh look, this interval here is contained inside your punctured neighborhood that you gave me, right? And it contains infinitely many elements. So I've more than exceeded your request, right? And if the guy says, oh, okay, I actually meant this interval. I meant this tiny interval here. And you just keep on going down. Right? You say, well, okay, I'm going to divide farther, divide farther, divide farther. That interval there contains infinitely many elements, and it sits inside your interval, sits inside your punctured neighborhood. So I'm good. Okay, so that's the idea. You say, okay, choose n, so given epsilon, choose n such that 1 over 2 to the n times the length of the initial interval is smaller than half of epsilon. So I've got A, I've got my epsilon neighborhood. Okay. And I'm going to go so far down the list of intervals that the length of my interval is less than half epsilon. Okay. Right? Then I sub n, right, which contains A, must lie in A minus epsilon, A plus epsilon. Right? Because the length of I sub n is less than epsilon over 2. Right? So the length of the length of my interval that I've chosen is less than epsilon over 2. Right? So it has to lie inside the punctured neighborhood. Right? And contains infinitely many points of S. Right? But then, so the punctured epsilon neighborhood of A contains infinitely many points of S. Right? It intersects S a lot. So what you see is that any punctured neighborhood intersects S, and so A is an accumulation point. And so this is the Bolzano Weierstrass theorem. Okay, that's it for today. You have an exam next time.